Assalamu alaikum students. Today we are going to learn about simple harmonic motion and circular motion. Let us read about it. Circular motion and simple harmonic motion. Let us study them side by side. As you can see, we have both the motion, the circular motion, as well as simple harmonic motion, or we can say mass attached to a spring system. And we see them in a form of graph as well. Let M Let a mass m attached with the end of a spring vibrate simple harmonically with the time period t, frequency f, and amplitude x0. As you can see, the displacement is an amplitude over here, and that displacement is represented by x0, which is the amplitude, and that amplitude is equal to the radius of this circle. Let's continue reading. The motion of the mass is displayed by M on the line BC with A as the mean position and B and C as the extreme position. Now we have points over here represented by C, B and A, where C and B are the extreme position from uh, the center of the mass of the system, and whereas this point A is the mean point or the midpoint of point B and C. We can draw point B and C in the case of circle as well. Assuming that C as the point of the pointer at t is equal to 0, it will be, or it will move so that it is at A, B, A and back to C at instant t by 4, t by 2, 3t by 4 and t respectively. Now for this we have the graph which is extending on the x-axis along, which is representing the time period t, and on the y-axis it is representing the amplitude, which is x naught to x, if we can say in other words the displacement from the mean position. Now in this case we have to study about a time period. Let's assume the time period is represented by a circle over here. Now we divide the whole time period into four parts. We start from here. Let's say at this point the time was 0. If we cover this much time, or we have spent this much time, which is almost 1/4 of the whole time, then what will be the value of t at this point? So at this point t has a value of t by 4. That means 1/4 of the whole time period has been covered. Similarly, if we have covered this time also, then we can simply say that t is half covered. That means total time period, half of the total time period has been covered over here. Similarly, if we look at this, and this much time is also covered now, so in this case t will be equal to 3t by 4. That means 1, 2 and 3 parts of the whole time period has been covered out of 4, so 3t by 4. And if even if this part is covered now, so it will be t is equal to t by 4 multiplied by 4. So because fourth part is also covered now, so this 4 cancel over this 4, so we have the total time period t now in this case. Now we can represent this whole thing as a 0, t by 4, t by 2, 3t by 4 and t. We can represent it in the form of radian as well by using the formula where theta is equal to the angular displacement, which is equal to angular velocity, which is omega, into instantaneous time t. As the body is covering a whole circle or a rotation, so we'll say 2 pi, which is the circumference covered in time period t, and this is the instantaneous time t. Now this is the formula which we have to focus right now at different times. So at t is equal to 0, what will happen? What will be the radian at that point? Theta will be equal to 2 pi t multiply, putting the value of t naught is equal to 0, we get 0 over here. So at 0 point t, or we'll get 0 radian. This is for t is equal to 0. What if t is was equal to t by 4? So t by 4, putting the value of t by 4 in the same formula, we get theta is equal to 2 pi divided by t multiplied by t by 4. So this t cancel out with this t. 1 2 ones are 2 twos are is equal to pi by 2 or 90 degree, we can say. So theta at time t by 4 will be equal to pi by 2. Now if we can separate this whole thing, yes. Now in this case we have, let's put t is equal to, small t is equal to t by 2. That means half the time has been covered now. Then theta will be equal to 2 pi by t multiplied by t by 2. So this t cancel out with this t, 2 cancel out with this 2. So at this point theta will be equal to pi. So at t by 2 the value of theta will be equal to pi. Now in this case we are moving towards the next point, which is 3t by 4. So let us put the value of 3t by 4 in this equation. So 3t by 4, theta is equal to 2 pi divided by t multiplied by 3t by 4. This t cancel out with this t. 2 ones are 2 twos are. So the value of this will be 3 pi by 2. So we put in the values of this 3 pi by 2 over here. Last but not the least, let's put the value of t equal to capital T. So for that, theta will be equal to 2 pi divided by t multiplied by t. So this t cancel out with this t. So our answer will be equal to 2 pi. Putting the value of 2 pi over here. So at t, it has covered the whole distance or whole circumference, which is 2 pi. Let us rub it off and move back to our situation in which the body has been synchronized. Both the bodies, like over here as well as over here, both the bodies are synchronized and they will move simultaneously like this. Like if we move and note down the time, that in this much time this mass m has reached from point C to point A, in the same time it has reached from point C to point A at this same time, and the same method, from the same position C it has moved to the mean position point A like this in the graphical method as well. So it has moved from point C at the extreme point to point A at this point. As we continue, it moved from point A to point B, let's say from here to here, and in a similar method it has moved from point A to point B, which is over here. Now if we light a shadow, like if we throw a light over here, then it will cast a shadow of this ball which is exactly underneath this mass attached to a spring system, which shows that as the mass was moving, the circle on the top was basically moving simultaneously with it. Now, if we continue moving like this from point B to point A, now in this case, we can see the body has moved back to its mean position. As you can see from here, the circle has moved from point B, if we consider this point B, to point A over here, and the same way point B to point A over here at time is equal to 3t by 4. That means if we convert this whole part, so this much time has been covered. Now for the last quarter of the circle, it will move back to its original position. That means from point A to point C, and from point A to point C over here, and from point A, which is over here, to point C, which is extreme point, x naught, drawn graphically as well. Now let us explain this whole scenario with the help of graph. Now this graph is basically representing the horizontal component of the mass attached to a spring system. Now as we know that if we are using a triangle and there is a vector form of that triangle, we are only taking the horizontal component over here. So a cos theta has to be used. And this graph is basically representing the same thing, the cos theta part. That means the cos at 0, at angle 0, theta equal to 0, it is equal to 1 or maximum. Then cos at 90 is equal to 0. At cos, you can say 180, it is equal to minus 1, that means in negative. Then cos 270, it is going to be 0, and cos 360 is again the maximum part. So this graph is basically representing the cos theta of the motion. This will complete one cycle of the vibration. As you can see, one vibration is completed in this case, or one wavelength you can say in this case. And x naught is equal to AB and AC. As you can see, x naught, which is the amplitude, is equal to the radius r and is equal to the amplitude. And in the same way, AB is also the same distance as that of the AC in this case. The concept of circular motion is introduced by considering a point P moving on a circle of radius x naught with a uniform angular frequency omega is equal to 2 pi over t, where t is the time period of the vibration of the pointer. That means in the same time when it moved from here to here, the mass moved simultaneously with the same angular velocity as that of the circle. It may be noted that the radius of the circle is equal to the amplitude of the mass of motion. That means in this case, the radius of the circle is quite the same to the amplitude of the mass attached to the spring system. Consider the motion of the mass projection of m on the diameter bc. That means if we consider this as a diameter over here, then if we light a shadow over here, it will move along the diameter as the body was moving in circular motion. Consider the motion of mass projection n on the diameter BC drawn parallel to the line of vibration of the mass in the figure. Now, this what we have already mentioned, that the mass will be moving along the circular motion as it is synchronized. Note that the level of mass B and C is the same as that the point B and C of the circle. That means this BC are representing the diameter of this circle. They are the same. Now, this is because we have to compare both the mass attached to a spring system as well as a circular motion. As m describes the uniform circular motion with the constant angular speed omega, that means as the mass was, or this point P was moving with the angular velocity omega, in a similar way, this mass was moving in the same uh, velocity but in a linear way. We are comparing a linear velocity with the angular velocity over here. M oscillate to and fro on the diameter BC with the time period t. That means the angular velocity omega is quite similar to the linear velocity of this mass attached to a spring system. Now, if we forget about this horizontal part, right, and now we are going to talk about the vertical part. We forget point A and point C in this case, and we are only focusing on the vertical part in this case. Now, in this case, the body is at point A, which is at mean position, which is same as that of the circle point. And now we are going to focus on the graph as well at this circle, that how this behaves now. Now, as it moves, as you can see, the mass also moves to point C, as body was at point, let's call this point A, and it moved from point A to point C. It moves to the extreme position in this case as well as in this case, and the distance from point A to point C, let's call that displacement, which is maximum, or we can say amplitude. So that is why the graph moves from point O to point x naught because it has displaced its maximum, and that displacement which is maximum is equal to the radius of the circle as well. But now we are joining the case of horizontal part, not the vertical part. As you can see, the horizontal part will not play a part in this whole scenario. We are not considering this horizontal part, only we are focusing on the vertical part. And this is point B, this is point A, and this is point C, only for the vertical part. Now, as it moves down again from point C to point A, now in this case, we can see that the body was at its extreme position. It went down to its mean position. From C point, it went down to A point, and in the same way, the circular motion from C point, it went down to A point, and it will continue to do so. From A point, it will go down to B point, and as you can see over here as well, the circular point is at point B. As we look in this direction, this whole thing is alongside P's. And in the same method, we can see in this case, the whole body has moved down, but in opposite direction. At point C, it was in upward direction, but at point B, as you can see over here, it is opposite to point uh, C. That is why it is in opposite direction in the graph as well. When it moves back to its point A, over here, if we remove it, when it moves back to point A from here to here, we can see that it has gone back to its mean position. It has gone back to its mean position, and it went back to its original position in this case. So it has moved uh, simultaneously with the mass attached to the system, but in the vertical case. Now, if we want to draw a graph of this motion, which is vertical, it will be like this. Now, what does this graph represent? Again, now in this case, again we have, let's say, four a vectorial diagram over here, and it is a y or ax, which are the two components, horizontal and vertical components. Now we are only talking about the vertical component, so it will be represented by a sine theta. So this graph is basically representing the sine value of this mass attached to a spring system, or a horizontal vertical component of the circular motion. Sorry. Now we can compare it over here, that in this case, at point 0 the sine 0 is 0, sine at pi by 2 is maximum, which is over shown over here, and the similar way sine is max 180 is 0 again, and at 270 it is negative, and at 360 it is 0 again. Now, assuming that the position of m at t is equal to 0, the position of m at the instant 0, t by 4, t by 2, 3t by 4, and t will be 0, a, c, and b, and a respectively. Now we can compare these two motions. A comparison of motion of mass m shows that it is a replica of the mass motion in a circle. Thus, expression of displacement, velocity, and acceleration of the motion of mass execute SHM. That means this mass attached to a spin system, it was executing SHM, and in a similar way, this circular motion is also representing SHM. Now, if we want to compare both horizontal and vertical components, now if we want to share it, that as you can see, both are moving simultaneously as they move along, and at the end they go back to their original position. I hope you enjoyed today's lesson. Inshallah, we'll meet again. Allah Hafiz.